Hello, this is E637. I'm Charles Bouman, and we're going to pick up on nonlinear filtering. Hopefully by this time you've recovered from the exam. Let's see. Yep. Okay, so I think we basically nonlinear filtering. I think I kind of spoke about this just very briefly last time, and I said that linear filters. Did I start talking about nonlinear filters at all? Oh no. Okay. So I'm starting from scratch. I couldn't quite remember whether I had started to talk about it a little bit. Okay. So linear filters are great in that you've used them to do, like for instance, restoration in the labs. And the thing that's great about them is that there's a lot of results that can be formulated that where you can get exact solutions to optimality conditions. So if you want to have minimum mean square error estimation with a linear filter, you can find the minimum mean square error filter. And as a matter of fact, even in more general conditions, you can get exact solutions to a lot of these kinds of problems. But the problem with linear filters is that they're very closely related to Gaussian models. So, and the reason that is true is that if you think about it, if you have two random variables, you have x and y. I'm forgetting in the lab, the thing you're predicting is y, or the distorted image is x, or the distorted image is y. I think this. Okay, it doesn't matter too much, I guess. So if these are jointly Gaussian.
Is that what you want? No.
So these random vectors, these are vectors. These random vectors are jointly Gaussian. What does it mean to be jointly Gaussian? It means that their density function can be written in a particular form that's parameterized by a covariance matrix, is really an inverse covariance matrix and a mean, right? So the other way of defining it is it's jointly Gaussian if you take any there's any linear transform of the data forms scalar values that are Gaussian. So basically, if for all theta, okay, if I take theta transpose times xy, I get a scalar random variable. So this would be z, okay. If this is always Gaussian for all theta, okay, then it's Gaussian. That's another way of specifying. There's actually, this has to be Gaussian and if it's Gaussian, it means its variance has to be greater than 0. Okay, so if this is a Gaussian random variable for all values of theta, then this is jointly Gaussian. The other way of saying it is that it has to be equivalent condition is that it has to have the form of the multivariate Gaussian distribution. So if that's the case, then the conditional expectation of y given x, okay, is going to be equal to ax plus b, where b is a scalar. B could be a vector if y is a vector. But in particular, if x and y are both zero mean, which is a special case, but it's really without loss of generality, because you can always subtract off the means, whatever they may be. So if these are zero mean, then it's just equal to ax. This would be zero mean case. So when random vectors are Gaussian, then the minimum mean square error predictor is linear. So there's this very fundamental connection between linearity and Gaussianity, I guess. Is that a word? I don't know. Gaussian random vectors. If something's Gaussian, then optimal prediction and filtering tends to be is linear. Well, it depends on how you define optimality. But if it, in the sense of mean square error, it is linear. So things that are Gaussian tend to lead to operators that are linear. And linear operators tend to implicitly assume that the things are Gaussian. So that's a very strong connection. So the problem is not everything is Gaussian. Well, maybe that's not a problem. Maybe that's a good thing, okay? Because it makes the world a more interesting place, okay? But the bottom line is, if everything were Gaussian, we could probably more or less get away with using linear operators all the time. But in practice, things are not necessarily always Gaussian, so you can't do everything with a linear operator. Well, you can, but you won't get always the best results. So, but the nice thing is that with the linear operators, as we saw, you got it's very attractive analytically, because you can calculate exact solutions to things. You can find very effective estimators for these linear operators. Just simply the space of all things that you can, the space of all operations is easily parameterized by a matrix, right? If you tell me you have a linear operator between two spaces, one space is n-dimensional and the other one's m-dimensional, it's a linear operator, then I know that space is parameterized completely by an m by n matrix. That's very simple. If you tell me that the conditional expectation of y given x is equal to f of x, where this is any function of x, so this isn't necessarily a linear function, then that's a huge set of operations, and parameterizing it is extremely difficult, right? I mean, there's various assumptions you can make to try to simplify it, but in general, getting a handle on that relationship is going to be very difficult. And as we learned earlier with training and testing methods, the more parameters there are in a model, the more difficult it is to estimate the parameters in a model, because it's very difficult to get enough data. So linear models are attractive because they work optimally with Gaussian data, and they're simple models for which there are closed-form solutions to calculate parameters. But they're unattractive because they make this assumption of it being Gaussian, which may be very unrealistic in real applications. So one way in which so basically most things involving most cases in which nonlinear filters can be superior involve some underlying phenomenon which is not Gaussian. So in images, that may mean edges, because edges are fundamentally not Gaussian. I mean, if you look at the distribution, even the monovariate distribution of, say, a single variable, which I talked about as being like taking differences between adjacent pixels. If you plot the histogram of that, you'll see that that is not a very Gaussian histogram for any real image. Okay, and and the reason is that the edges produce very strong tails on those distributions. So edges are a non-Gaussian kind of a phenomena. Impulsive noise. So if you have Gaussian noise, that's fine. So that might be the kind of noise that you would get if you had an amplifier and a low noise. Let's say you have a camera that's designed to work at very low noise levels. So you might get thermal noise from basically a shot noise from the electrons. That can be very accurately modeled as Gaussian. But other kinds of noise that might result from some kind of distortion that's nonlinear, like you have some impulsive noise, and that might be due to dropouts or some binary effect that happens when some random event occurs. So that's heavy-tailed noise, and it may not be modeled well as Gaussian. So when either the distortion is non-Gaussian, or when the image statistics itself are non-Gaussian, then the optimal estimator may not be linear. The problem with the nonlinear cases is it's hard to design. So a general theory of nonlinear filters is not very easily created, but nonetheless there's some interesting things that can be said, and we'll sort of touch on a few ideas in nonlinear filtering, although this is really just a kind of a high-level view of the field. I mean, there's a lot more that can be done. Okay, so a filter is linear if it obeys this kind of equation, which is for all alpha and beta. X1 is one image that's input, and X2 is another image, and then the corresponding outputs are Y1 and Y2. So if the scaled superposition of the two images produces the scaled superposition of the output, it's a linear filter. And in general, if it's a linear filter, then this is the most general output, because this is basically just representing the input between X, the input-output relationship between X and Y, as this is like a matrix H. Okay, so you could think of it as a space-variant point spread function, because it also can be viewed as the rows of the matrix H. So if you have I should have written it as Y equals HX. So you have a tall vector here, and then you have a matrix here, and you have another tall vector here, and then each row of this matrix appears to be like an impulse response. So if it's a Toeplitz matrix, where the rows shift with position, then that would be corresponding to a linear space invariant filter. But if it's not Toeplitz, then the H's are not shift invariant. So now homogeneous filter is a weaker condition, which is that if you scale the input, the output scale. So it's often useful to have this, that the image is scale invariant. Any nonlinear filter is scale invariant. So a simple nonlinear filter is the median filter. Basically, what happens is I shouldn't have that here. The median filter, you take some window about a pixel and you take the median. So you have an image here. Okay. So in general, in a nonlinear filter, you take a window here. It's just like what you did in the lab, only now the operators may be nonlinear. So you have a point here, and you replace this point with that value. One thing you have to be careful of when you implement this is that you don't actually store the result. And I bet a good number of people in the class did this, and this is one of the things that's great about the labs. You do it. If I tell you, you'll never remember. But if you actually create the bug yourself, then you'll remember for the rest of your life, because it takes you so long to debug it. But what happens is if you calculate the output at that pixel and you store it back into the same location, right? It doesn't work. How many people did that when they implemented the lab? I'm just curious. Oh, come on, be honest. If nobody puts up their hand, then I know you're not telling me the truth, because I know that's what everybody does, right? You take the same frame buffer, right? Memory. You calculate the output and you store it right back in the same place, right? Oh, come on. At least one person did it. Be honest. Nobody did that? No? Oh, gosh. Maybe you guys are getting smarter. Oh. Usually somebody does that, and then you get, so it's like an IR filter, basically, is what you get then. But, so you have to store this here. But now you just replace this linear operator with a nonlinear operator, okay? So what happens? So now one nonlinear operator you can do is do the median. Everybody knows what the median is. If you have an odd number of points, you throw out the largest and the smallest, the second largest, the second smallest. You sort them, right, from largest to smallest, and you take the middle one, right? So that's the median. So, so here would be an example. If the input's X and the output's Y, the median of 0, 0, 1 is 0. So this is your input sequence, 0, 0, 1, 1,000, 1, 1, 2, 2. So the 1,000 doesn't look like it belongs there. So the median gets rid of that, but it doesn't smooth out the edges. That's what's sort of nice about the median, that it preserves edges, but it gets rid of impulsive noise. So it's an example of a potentially useful nonlinear filter. Is the median filter homogeneous? I mean, is it linear? It's not linear, okay? It's not linear, so let me see. I'll give you an example. Is it homogeneous? Yes, because if you scale the input, the output scales. But it's not linear, so let me give you an example why it's not linear. So if we have the input, so if the input 0, 0, 0, 1, 0, 0, 0, okay? I'll put another 0, okay? The output there is just 1, 2, 3, 4, 5, 6, 7, 8, okay? Okay, that's if you apply a median, say a 3-point window median, right? Because if you take the median of those 3 points, the median is 0, so it's all 0, okay? So if I have 0, 0, 0, 0, 1, 0, 0, 0, right? That has the output, again, 0, 0, 0, 0, 0, 0, 0, 0, okay, right? Now, if I sum these two together, if I add them, then I get 0, 0, 0, 1, 1, 0, 0, 0, right? So the output of that is, if I apply the median filter, is going to be, actually, it's 0, 0, 0. That'll be, at this point, it will be a 1, right? Mm-hmm. 1 and 1, and then 0, 0, 0. So this is not equal to the sum of those two, right? So this is not a linear system because the sum of the superposition doesn't hold, right? If I apply the operator to this and I apply the operator to this and I add them, it's not the same thing as if I add them and apply the operator. All right? So it's not a linear filter, okay? Let's see, median filter. Okay. So now, of course, signal processors are never happy to just leave things alone. It was simple enough. But that's like not good because now we're not needed. So we have to find some way of making it all more complicated. So instead, I'm going to introduce an optimization framework for the median. Okay. So to produce the same result in a more complex way. Okay. So one way of thinking about the median is you take the median of a set of points. Is what you can do is introduce a function. And the function you can introduce is the absolute value function. So you take the difference between theta and all the points in the neighborhood. So this is summed over all the points in the neighborhood. Okay, hold on. This is summed over all the points in the neighborhood of the pixel. And you take the difference between theta and each point in the neighborhood, you take the absolute value. And you say, well, what's theta? Well, theta is just an independent variable that I'm going to adjust that will change the value of this function f. So now the way I'm going to select theta is I'm going to minimize f with respect to theta, and the corresponding value I'm going to call y. Well, it turns out, so differentiating, okay, now I know this is a little bit dicey or unclear or a little unsavory, you might say, maybe is a good word. But I'm going to differentiate this function. That's problematic because the function isn't differentiable, okay? But it's only not differentiable at a point, so let's not worry about it for the time being. So we differentiate this, and we get this expression here. So the derivative then of absolute value is basically the sine of the difference, except for at 0. So we want that to be 0. So we set it equal to 0. So that would be the value of theta that minimizes this function, okay? So the function kind of looks like this. It doesn't actually kind of look like it. It looks exactly like this in this particular case. So now to plot the function, we have to actually assume some values. Otherwise, we can't plot it. So let's assume that the values in the window are -1, 0, and 1. And that, I'm sorry. Okay, the window is -1, 0, and 1. So we're taking the point to the left, to the right, and the current point, okay? The values in the window are -2, -4, and 5, okay? So if we plot that function, which is the sum of the absolute values of the difference between theta and those values, we're going to get 3 inflection points. One at -2, one at -4, one at -2, and one at 5. And so, if you have like theta minus x, right? The function you get here, this is x, and you get a function like this, right? So we'll call this x1, right? And then if you have plus a theta minus x2, right? And so let's say x2 is here. So then you're going to get this, right? So if you add those together, you get something like this, actually. Oops. I'm not drawing it very well, but something like that, right? So, oh, that's kind of going off this. Now, one thing is that these are called convex functions. It's convex. Well, I think people intuitively know what the word convex means, like a convex surface. So this is a convex function. When you sum convex functions together, you get other convex functions. The technical definition of convex is that if I take 2 points, so, convex. When I take 2 points, this function is said to be convex. If I take 2 points, so I'll call this A and B, and I take any 2 points, and I draw a line between them, then the line falls above the curve. So that means for all lambda in the interval 0, 1, all right, and for all A and B, a member of R here, that we have that if we take a lambda times f of A plus 1 minus lambda times f of B, and then we take, on the other side, we take the f of lambda A plus 1 minus lambda B. So that's this point here, right? That's lambda A plus 1 minus lambda B, right? That, if you take that point, this is this point here on the right. So this is the right-hand side. And over here, this is the left-hand side. So the left-hand side has got to be greater than or equal to the right-hand side. So that's convexity. This is the definition of convexity. And if it's a strict inequality, as long as lambda here is in the open interval, then we call this strictly convex. So these functions here are convex. And when you add together convex functions, you get convex functions. It's actually a little counterintuitive that that's true, but it's true. It's very easily shown because you just apply this to the functions you're summing together, and then basically the inequality constraint for the sum of, if you have two equations for two functions and you add them together, then you show that the sum of the two functions is also convex. So this is a convex function. So you can find its minimum, and the minimum is here. It falls at the point -2. Okay? So -2 is the median. So this is just a complicated way of finding the median. Okay? Now, if you differentiate the function as I described, then what ends up happening is that at each inflection point you jump, the derivative jumps. So the derivative is discontinuous. Okay? So it's discontinuous at -2, -4, and 5. In between it's well defined. So you look for the place where it jumps across 0. And you can, if you imagine that the bottom of the function was actually just rounded a little bit. So instead of it being a perfect V like this, there was just a little bit of rounding at the bottom. If there's a little bit of rounding at the bottom, then when you look at the derivative, what happens is instead of it being discontinuous, it just goes like this. And there's just a little bit of transition there. In that case, the derivative could be thought of as existing, and where it crosses 0, that's the minimum. So this is another way of calculating the the median. So you'd say, well, who cares? Why would you make a simple problem complicated like this? Oh, well, because there's some interesting generalizations one can make when you reformulate in this more general framework. Okay? So the interesting generalizations are this. The problem with... okay. Well, I'm going to talk about the interesting generalizations in just a moment. But if there are an even number of points instead of an odd number of points, then you have this unpleasant situation where if there's an even number of points, the median's not so well defined because the minimum could have fallen anywhere along here, or it did fall. It's non-unique, right? So, one solution is just to take the point in halfway in between. But it's kind of a detail. Okay, but what you can do is you can do a thing called the weighted median filter. And the weighted median filter is a generalization of the median filter. So in the median filter, you minimize this cost right here where you'd... I need a slightly thinner pen. So where you take out that weight right there. Okay? That would be minimizing this function as a function of theta would produce the median. So now a natural thing to say is, well, maybe not every point should be weighted the same. Certainly in a linear filter, you have different weights for the different pixels. So why should they all be the same? Well, the problem with the median is you're not exactly sure how to generalize it. How do you take the median where you weight the different values you're taking the median of differently? It doesn't obviously come to mind as to how one might go about doing that. But in this more complicated framework, we now get the benefit that it's more general because we can put weights in here in this cost function, and we can solve the minimization of this weighted cost function. And that has the natural interpretation that when the weights are uniform, we get the regular median, and that when the weights increase, that pixel's more important to the overall calculation. So it achieves the desired result. If I differentiate it, then I get an expression that looks like this. Now the only thing is the signs, this function here, the weight in their contribution to the overall derivative varies. And so now what the thing is, we want to solve that this is equal to 0. But again, we have the problem that the derivative of this function doesn't exist when theta equals x. Now you would say it's not a big problem because it's only one point and we have the entire real line, okay? So as long as we're anywhere other than just that one point, okay, we're good, okay? Except for, guess what? It's just like my kids. If there's any place they could get into trouble, they will, okay? So it's the same thing. It's the Murphy's Law event, all right? Which is that the theta ends up being exactly at the point where you had a problem. And the reason is that if you look at the derivative, if you look at the function, if you have something with points on it, right, like a cube or something, and you drop the cube, guess what part hits first always? The points, the edge. You always chip the edge on your furniture first, right? Because when you go to do the optimization problem, with high probability, unless you just happen to hit, the probability of you hitting exactly flat like that is like the same probability that you're going to throw a dart and you'll hit pi. Okay? So it's 0. So you're going to more than likely hit one of those points. So even though those points are sparse, they're problematic. But you can do this by basically looking for the place. The way I like to think of it is like this: that you're trying to find you're trying to find the place where this crosses 0. Okay, so you want to look at the position along here until you find the place where you're balanced. So this is the way I like to think about it, actually. I don't know. Okay, that with the weighted median, what you do is this. Did you guys implement? You implemented the weighted median already, right? So what you do is you do this. You say, okay, I'm going to have. I start off with x1, x2, x3, right? So I have x1, a1, and then I have x2, and I have a2, and I have x n, a n, right? Now what I do is I sort them so that these x's are in order from smallest to largest. So I'm going to put some parentheses here. The parentheses mean that I've resorted them. I did a permutation on them so that the x's are ordered. And whatever permutation I use the same permutation on the a's. So the a's are not ordered. Okay? So the a's are not ordered, the x's are ordered. Now what I do is I take the a's and I have a scale. Okay. I don't know how to, okay, and you put things on the two sides of the scale, and the scale tips this way or it tips that way, right? Okay, so I start off with all the A's on one side of the scale, okay, and then I take A1, the first A, and I put it over here, and I see if it tipped, and then I take A2 and I move it from here to here. There's going to be one of these A's that when I move it over, it's going to tip. Okay? The A that tips the scale is the A, so let's say that there's some particular A. So that's going to be A, so it's going to be A, I star. So it's I starth, okay? That's going to be the A that tips the scale. So that one, I take the corresponding X I star, and that's my output. But you guys did this already, so you're experts on it, right? Did you have any trouble when you were implementing this? It was a little tricky, but eventually you got it, right? Because perseverance is an amazing thing. By the way, how many people know the answer to problem 3E?
Oh, from the exam?
Yeah. Okay. Don't talk about it because they haven't all been handed in yet. Okay. Computation of weighted median. So this is just codifies this mathematically. Okay. Now, comments. Okay. So weighted median is kind of an interesting algorithm because it's a generalization of the median and allows you to optimize the values of the weights to get the best performance on a nonlinear filter. There's lots and lots of nonlinear filters, so I don't want you to think that the only nonlinear filters are the median and the weighted median. But I just wanted to give you a flavor of some methods, and also this idea that you can how you go about trying to parameterize the set of nonlinear filters, and also I have a sort of a hidden agenda, which is that weighted medians are closely related to a large class of other things that have gotten really a lot of interest in recent years in imaging. So I'm using it as a segue into that. And that's so there's this connection to this other thing called M-Estimators, okay? And M-Estimators are related to something else which are been widely used, or have become more widely used, which are called Markov random fields. So we won't get into the Markov random fields, but I at least want to introduce M-Estimators because they're related to this weighted median concept. So in general, one might have the problem that they have a set of values, right? You have x, say x1 through x. How many am I going to have in here? X, p, okay? So the p values, okay? And you might say, I want to calculate. I'm assuming that these are all independent and drawn from a single distribution, and somehow I want to find let's say, for lack of a better word, mean. Mean may not be a good word, because it could even be the case that these x's don't have a mean. It could be that the mean doesn't exist. But somehow I want to find an estimate of their center, okay? So how am I going to do this? So you might say, well, I'll take the average. Well, the problem with the average is that the average can be excessively weighted by one outlier value, right? You could say, well, I could take the median. Well, the median's okay, but it might not be the best result, because the problem is it might be that, for instance, a typical situation would be that these are mostly all Gaussian, except for there's a few crazy values that have been inserted in there, right? Mm-hmm. So what's the best thing to do? Well, well, first of all, in order to be able to answer the question of, well, what's best, you would need to have the distribution, okay, which may not be available. And even if you have the distribution, what's best is going to depend upon your criteria of goodness, okay? Now, just to give you an idea that, like, how difficult a problem this could be, if I say, so let's say that these things are all distributed as P of X minus theta, okay? So that's the probability distribution, okay? And theta is unknown, okay? So now if I take the estimate theta hat equals 3, okay? That estimate is the best estimate I can get when theta is 3. Okay? So if I'm like, if I'm at a fair, okay? And when you go to a booth and they have the person who tries to guess your weight, okay? So if I always guess 125 pounds, that's the optimal estimate if the person happens to weigh 125 pounds. But like intuitively, it doesn't seem optimal. I mean, it doesn't seem like a good idea to make your estimator independent of the data. But it nonetheless is optimal if that answer is right. So the problem of optimality of estimates is tricky, because finding a uniformly best estimator is basically not possible. You have to put some further constraints on it, and people talk about they want an unbiased estimator. Okay, so the problem with always guessing 125 pounds is it's biased. It's biased towards 125 pounds. So there's so it's not a very clear-cut situation, okay? But nonetheless, it's a very important problem that people have spent a lot of time thinking about. It's a very simple problem, but it captures a huge range of practical situations, and it's very impactful, okay? But one class of estimators which was proposed a number of years ago and is, I think, quite useful, and also just conceptually illustrates an interesting approach, and keeps reemerging as new fields and keeps getting reinvented in different ways, is what are called M-Estimators. And the idea here is this: your idea is that you pick a function, rho of delta. It should be a symmetric function. All right. So, oh no, what am I doing? I put the minus in the wrong place. Okay, and that typically rho of 0 equals 0, really without loss of generality. Okay, so it's going to be some function like this, say. Okay, and typical choice for the M-Estimator is that typical choice is going to be rho of delta equals, say, delta squared, or rho of delta equals delta to the p, or rho of delta equals the absolute value of delta, or it could be like, well, we'll get into some other choices later, okay? Otherwise, it would seem somewhat unmotivated. But these are simple functions, right? And then what you do is you say, okay, my value of theta is going to be the value of theta which minimizes the sum from I equals 1 to p of rho of theta minus x of I. Rho, that's a rho. Okay? So you try to find, so this is a cost function. You can think of this as energy minimization. So you can think of this as rho as energy. If rho is, if you pick delta equals rho equal to delta squared, then this looks like a regular spring. This is a simple model for a spring in physics, because the energy stored in a spring is proportional to the displacement of the spring squared times a spring constant. Okay, so now if you then differentiate it, you differentiate this, you get that this is the sum from I equals 1 to P of rho prime of delta minus xi, okay, is equal to 0 at rho equals, or theta equals theta star. So this is now the equivalent equation you need to solve. So you can solve it as a rooting function where you find the solution to the minimizing the derivative, or you can do a minimization function here, okay? So this is the same form we have for weighted median. So if we have, in this case, we have weighted median. If you take this case, in this case, if you take the derivative, you'll get linear operators, so this is going to be the mean. Here you'll get something between the median and the mean. So if I differentiate, if I take rho of delta equals delta squared, and I differentiate it, then rho prime of delta is equal to 2 delta. And then if I plug that into the equations, I get that the sum from I equals 1 to P of 2 times theta minus x of I is equal to 0. And this is for theta equals theta star. So this is mean case. All right, so if I solve for this, I get that the sum from I equals 1 to P of theta is equal to the sum from I equals 1 to P of xi. So this is equal to theta times P, right? So this is going to, so theta star here is equal to 1 over P times the sum from I equals 1 to P of xi. So that's the mean. All right. Now, if I take, and you could do a similar thing for the median. Now, what happens typically is that if we have that, so we take the function rho here, and we take the function rho prime, the derivative of rho, and we plot this, and we plot this. A typical case is that this is called the potential function. And the derivative of the potential function is called the influence function. So why is this called the influence function? Well, because if I differentiate it, I get an expression like this. I get something like this. This shows this expression here is, this axis here is delta, and this is delta. Remember, delta is equal to theta minus xi. So it's the difference between the value I'm estimating and the pixel. So what this function says is when I try to, this is like an energy minimization function. I want to minimize this expression, which is the difference squared between the value and the pixel. So if I perturb the pixel, the derivative here tells me how much that perturbation is going to affect my result. This is the influence. So this is how much your result is influenced by that pixel. And now the problem here is that here in a linear operator, any one value can have an infinite influence on your pixel. So just if you have one crazy value, like sometimes I've had this experience where a student was doing research and somehow they got like a floating point number and a fixed point number mixed up or something like that. So they basically had random binary garbage into their variable, okay? So all the other variables are like 3, 2, 17, 14, and then one of them is 6.57324 times 10 to the 273rd, okay? Well, guess what? All those other variables don't matter. Those values don't matter because that one value that's extremely large or extremely small will completely dominate the result. So somehow you don't ever want to believe just one value that much, right? So what you do is you say, okay, look, if it's greater than some amount, I'm going to clip it off. If I do that, when I get to that corresponding value, and that value is going to be at t, but beyond t, I don't believe it anymore. And here at t, I get this. This is t. It's a little more subtle to draw here, minus t. This is minus t. It's like that. So this is called the Huber model, Huber function. Oops. Function. So it basically clips the mean. The nice thing about this is a convex function, so you can compute the global minimum, and it has this sort of nice framework for understanding what's going on. It's an extension of the weighted linear, the weighted median. Okay. Another example. So that's actually another example is this example right here, where you clip off. So here, above some value, you just completely ignore the value. This is kind of a more severe choice. Yeah? Excuse me? Very good question. Well, that's a problem, okay? Okay? In some cases, it may be motivated by the physical problem, okay? In some cases, you may need to actually estimate that as part of the overall problem, okay? But, yeah, I mean, I'm not pretending to have solved all the problems here, okay? What I'm really just doing is introducing some frameworks for thinking about it. But this is a very powerful framework, and it can be extended to, I mean, it seems very simple, okay, and it is, but it can be extended to much more complex scenarios. If you take E6, this is an unabashed plug for the course, I guess, but what am I supposed to tell you? So if you take ECE 641, we cover this material in some detail, and if you're interested in it and don't want to take the course, I can point you to some web pages where you can get information. But yeah, this is sometimes called the broken spring model, because it's as if this was a spring, but when you got to a certain point, the spring breaks because the amount of energy, it stops mattering, okay? But then when it comes back, the spring like repairs itself and reattaches. So it's sort of an unusual kind of a thing, you know? It's a highly nonlinear kind of a response curve, and you know, if you have, it's a little bit like silly putty. Have you ever played with silly putty? You know, you can get this stuff you buy at the store. It's not that expensive, so if you want to do an experiment, you can go get it. Okay, and then you can get like the newspaper, and you stick it on the newspaper, like on the comic strip, and you pull it off, and you see the comic strip, and then you can stretch it out. It's sort of fun, but when you pull it, it sort of will pull, and then if you pull too hard, it snaps. Right? So this is kind of that kind of nonlinear behavior, you know, and this is not a convex function, you see, because that is falling below the curve. So because that's not a convex function, the solution to that optimization problem can be very complex, particularly if the dimensionality gets high, because you can get local minimum in the overall cost function when you sum them together. So here, so you can get a function which looks like this. So you can be over here and not realize that if you moved over here, you'd have a better solution. Mm-hmm. But in this case, the Huber function I mentioned already, that is convex. So optimization of that is more straightforward. Yeah, and I think that's pretty much it. So are there any questions? In the next section, we're going to start digital halftoning. So I guess we're right at that break point. So if I'll see you on Wednesday, and have a nice few days. Thanks.